breast cancer. The project aimed to design a computer-aided detection for early detection of the breast cancer. Why that in particular? If we look at the commercial market in the US, for example, the CAT in US is very expensive. It starts at 30,000 and reaches 200,000 per license. And the second problem is it comes bundled with the hardware. So every vendor, for example, Fuji or Siemens, when they produce a machine for mammography, they produce and develop its own CAD, so it cannot be used in other machinery. So these are the two problems in CAD internationally. So our objective was to develop a computer-aided detection system software that solves these two problems. It will be much less expensive. Second, it can be used in detecting cancer from images coming from any other mammography machine. And these are the two keywords. It's less expensive and widespread. So this is what we mean by affordable CAD. Less expensive and widespread. The product, just before talking about the science and the algorithms and this stuff and accuracy, the objective was to produce just a DLL, dynamic link library. So all of the science, image processing, pattern recognition, algorithms, all of the stuff is encapsulated in just one library that can be called by any company or any vendor or any researcher probably. So the product is, in a nutshell, is a computer library, dynamic link library. Just you can call, find microclasification, find cancer, mark region, and so on. For example, all of the image viewers produced by different companies. Image viewer is a simple software that radiologists use to annotate images and see lesions and stuff. This software does not have CAD capabilities, and this is where LeapCAD comes in. LeapCAD is just will be callable by this image viewer to use its CAD detection capabilities. This is an example for the model. So LeapCAD is a product. It's produced by MES, for example, in our project. There is a company called Munkhfض having their own image viewer that does not have CAD capabilities. They take LeapCAD, incorporate it in their software, and deploy it in hospitals or clinics. For example, this is a real example in the Arabi hospital here in Egypt, and there is some collaborations with some companies abroad. Let's talk. Actually, I forgot to mention at the beginning that this talk is intended to be a little bit high level without delving into the deep details of the technicalities and algorithms because of the time. So the performance of LeapCAD, of our CAD, is as this. If this is the performance of literature, and this is the performance or accuracy of US CAD. This is actually our performance. It competes the commercial CAD in US and literature. So the CAD, our CAD has two major functions: detecting masses, detecting microcalcifications, and these are the main two problems or main two cancers in humans. And third, gives or produces image enhancement. So, for example, this is a mass detection. This is a kind of a mass. It marks the mass. This is the accuracy of literature, and this is the accuracy of LeapCAD, and this is the accuracy of commercial systems. Let's take a closer look at this. For example, this is the best algorithm in literature. It says its true positive detection is 95%, for example. This is 65% when it produces two false markers. This is a very important issue in detection. as you know, you cannot, in any detection problem, you cannot give just one number. You cannot give just a true positive. You say my accuracy or my sensitivity is 95%. So, by the way, anyone among us can give 100% in any detection. If you do not combine this with the other kind of error, which is the false positive, there is no meaning for the true positive. Otherwise, you can simply just close your eye and diagnose everyone as diseased. Definitely, you will classify the 100 disease as 100 disease. But on the other hand, you commit full error that is sending everyone to be diseased while it's not. So you have to combine those two numbers. So this is the accuracy of the best algorithm known in literature. You get 65% at almost 2 false markers. The LibCat produces 0.85 almost at 1 false marker, and at 2 it raises to 90%, which is much higher than what is known in literature. And if compared to the commercial product, there are 3 known in US, Image Checker and ICAT. It is very close and competes with them. I will show a comparative study, right? This is a comparative study between LibCat and commercial products. For example, this is the current version of LibCat. This is one of the commercial products called Second Look. This is the third one. This is the third one, Image Checker. So we are higher than all of them and very close to the best algorithm in commercial cats. It's called Image Checker version 8. So we are very close to the boundary also. I will go back one. Okay, this is for one kind of cancer which is called mass detection. The second kind is microcalcification detection, which is more subtle than the mass detection because it accounts for very little deposits, calcium deposits, hidden underneath the tissue of the breast. So, for example, this is an image of the breast. This is a very dense and fatty breast. And underneath these tissues that you cannot observe, there is a group of deposits, calcium deposits, called microcalcification, and this is a detection of LibCat of these ones. For the accuracy, for example, this is a commercial product, Image Checker and Hologic in US. Image Checker produces 100% at 0.13 false positive. We produce 97% at 0.5. They are better, but however we are very close. And this is the third functionality of LibCat. As we recall, we said LibCat has 3 functionalities. Number 1, mass detection, microcalcification detection, and image enhancement. Image enhancement is an aggressive filter that filters the image so that a radiologist can diagnose and investigate the image just by eye. It does not need automated detection. So this is, for example, an image without aggressive filtering. This is after applying the aggressive filtering of LibCat. So this is almost the research that concluded and produced this commercial product. This current research that we are trying to establish to boost the accuracy and boost the detection capabilities of LibCat to detect other kinds of abnormalities like architectural distortion, like asymmetry density, like skin thickening. Those are kinds of cancer as well, but constitute almost maybe less than 5% of the cancer cases. So this is why we deferred this kind of research a little bit, but we are trying to establish it. Current publications are those 3. We postponed actually publishing the details of algorithms until we get the patent. We applied the patent. It is under filing these days as we speak right now. And we started in writing the paper, the technical paper that describes the details of the algorithms. This is currently in processing, international patents in US and Europe. The next step in parallel to the research